Recording. Okay guys, so let me see record. Okay, recording. Share my screen. I think it's sharing. Let me just be sure. Stop sharing. Yes, sharing. I think, is it recording? Stop recording. Okay, it's recording. Let me just close all of this. Okay, so this is the last thing we are going to talk about this semester. ARDL. You already did it with Nigauja on Tuesday, so I will just add what I can add today. Okay, so today we'll do ARDL. What's the full meaning of ARDL? Auto-regressive distributed lag. That's the full meaning. Okay, so far what we have done for the semester, like after the midterm, and we started with time series. Like I told you guys, the first step in time series analysis is always to run your unit root test, because if you run your unit root test, you will be able to determine the order of integration of your variables. And depending on the order of integration of your variables, you will know what method to use. If I can show you something, let me see. Okay. Let's say we run our unit root test and we have the order of integration of our variables. Now we can have any of three situations. We can have a situation where all variables are integrated of order 0. I have a situation where all variables are integrated of order 1. And we can have a mixed order of integration. I've mentioned this several times. Mixed order of integration means some of the variables are integrated of order 0, while some of them are integrated of order 1. So we can have either of these cases after running our unit root test. Of course, if we have this case, if all of our variables are integrated of order 0, which means there is no unit, there is no, there is no unit root, it means all of them are stationary at level, then in this case, we can directly use basic regression, which is our ordinary least squares, as we know. But then, if we have a case where all our variables are integrated of order 1, that is I1, which means they have a single unit root each, that is, they are non-stationary at level, but they are stationary at first difference, then of course, in this case, we have to do co-integration. Do Johansen co-integration tests. Of course, there are many co-integration tests, but Johansen is like the famous co-integration test. Now, if we have a mixed order of integration, some of the variables are I0, while some of them are I1, then we have to do ARDL, auto-regressive distributed lag. That is the method we'll use. So now, one thing I'll let you know is that With ARDL, we can also do ARDL if all our variables are I1. So don't feel like we can only do ARDL if we have a mixed order. Even if we have all variables I1, we can still do ARDL. But now I'm insisting, if we have a mixed order of integration, then ARDL is the only solution. We cannot do co-integration. The only thing we can do is ARDL if we have a mixed order of integration. But if everything is I1, then we can do co-integration. We can still do ARDL as well. If everything is I0, then no need to do co-integration or ARDL. Just do basic ordinary least squares, basic regression, because there is no unit root, right? Okay. Now, let me say something about this case. If all our variables are I1, then co-integration, Johansson co-integration is a better method than ARDL. Of course, we can also do ARDL. The Johansson co-integration is a better method. Why? Because the asymptotic properties like this, Johansson co-integration has better asymptotic properties than ARDL. So it is a better method if everything is I1. But if we don't have sufficient number of observations, if our sample size, we don't have a high number of observations, then I will recommend ARDL. Why? Because ARDL has better small sample properties. So if your sample size is not really too big, then I will recommend ARDL. But if you have a good sample, then Johansson co-integration is better than ARDL if everything is I1. But then whatever the case, you can do both methods. Typically, what people do in studies is you will rarely find a study where they use a single method. Now, people use many different methods in their studies. So for instance, if you're carrying out a study, you run your unit root tests, and all your variables are I1, you can use both methods. For instance, you can say, okay, Johansson co-integration is your main method. Then you can use ARDL as a robustness check. You can use ARDL to check the robustness of your results. What do I mean by robustness of your results? For instance, let's say you do co-integration. Let's say all your variables are I1, you do co-integration. Remember, co-integration will only tell you if there is long-run relationship or not. Johansson co-integration test will only tell us if there is co-integration or if there is no co-integration. And you know, co-integration means long-run equilibrium relationship. It will only tell us if there is long-run relationship or not, but it will not give us the coefficients. If we find co-integration, that is, if we find long-run relationship with Johansson co-integration test, if we want to get the long-run coefficients, we need to do the vector error correction model. It is the vector error correction model which will actually give us the long-run coefficients. With ARDL has this advantage in that it does not only tell us if there is a long-run relationship or not, but it also provides the coefficients. So ARDL will tell us if there is long-run relationship or not, plus it will provide the long-run coefficients. So this can be like another advantage of ARDL over Johansson co-integration. Johansson only tells us if there is co-integration or not, but it does not give us the long-run coefficients. If we need the long-run coefficients, we need to do vector error correction model. But ARDL tells us if there is long-run relationship or not, and at the same time, it also provides the long-run coefficients. So let's say all our variables are I1. We can use Johansson co-integration as our main method. If we find co-integration, then we will use the vector error correction model to get the long-run coefficients. Then we can also do ARDL as a robustness check. That is to check if our results are robust. If ARDL tells us that there is long-run relationship, then it means the results of the Johansen co-integration test are robust, because the co-integration test told us that there is long-run relationship, and ARDL has also told us that there is long-run relationship, so we can say this Johansen co-integration test results are robust. And then now, if the VECM here told us that maybe the independent variable has a positive impact on the dependent variable, positive and significant impact, then we'll come and check the long-run coefficients from ARDL. If it is also positive and significant, then we'll say these results are robust. But if this one is maybe negative, if this one VECM is telling us that maybe positive and significant impact, and then maybe ARDL is telling us that negative impact, or maybe positive but not significant, then it means our VECM results are not robust. So you get the whole idea about robustness. You're just trying to see if you get the same results using a different method. Johansen co-integration test has told us that there is long-run relationship. If we use ARDL, can we still find long-run relationship? If we also find it, it means our Johansen results are robust. But if we don't find it, it means the results are not robust. Vector error correction model has told us that independent variable has significant positive relationship on dependent variable. If we use a different method, ARDL, can we still find the same significant positive relationship? Of course, maybe the coefficients will have different values, but then is the relationship positive and significant? If it is still positive and significant, it means our VECM results are robust. So typically in a study, they use different methods. They have a main method or some main methods, and then they use other methods to check their robustness. So you can use both methods if everything is I1. Understood? Okay, so that is it. So we have seen basic regression. We have seen co-integration and VECM. So we are going to see ARDL now. Okay. So before seeing ARDL, I already mentioned some advantages to you. I will just show you again. I made some notes here. So you see, the ARDL can also be applied in situations where all variables are I1. So of course, like I told you, we can do ARDL if we have a mixed order. But even if everything is I1, we can still do ARDL. But know that if everything is I1, co-integration Johansen is the best method, but we can also do ARDL. If we have a mixed order, then ARDL is the only solution. It is the only method. You cannot do co-integration. Because remember, in order for us to do co-integration, all our variables must be of the same order. You cannot have a mixed order. So we can also do ARDL if everything is I1. One advantage of ARDL is that it determines if there is long-run relationship, similar to co-integration tests, and at the same time, it also provides the long-run coefficients, similar to vector error correction model and these other methods which you see at PhD level. This is dynamic ordinary least squares, fully modified ordinary least squares, canonical co-integrating regression. So don't bother about this. You will see them at PhD level. But the bottom line is that why Johansen only tells us if there is co-integration or not, and then VECM provides the coefficients. ARDL tells us if there is co-integration or not, and at the same time, it provides the coefficients. That's an advantage of ARDL. Another advantage of ARDL is that it allows different variables to have different lags, and it has good small sample properties. Remember, I told you here that why Johansen is a better method than ARDL if everything is I1, because Johansen has good asymptotic properties. But if your sample size is not big enough, then I will recommend ARDL, because ARDL has better small sample properties. It works well, better than co-integration tests if your sample size is small. And here we have it. ARDL has good small sample properties. Okay, so this is the ARDL model. It was suggested by Pesaran and some other guys. in 2001. So this is the model. In this study here, my dependent variable was carbon dioxide, and here I had financial development, renewable energy consumption as independent variables. So I had just 3 variables in this model. Dependent variable carbon dioxide, independent variables financial development and renewable energy consumption. So in your own study, you can adapt it. Let's say your dependent variable is something else. Maybe your dependent variable is income. You can just put here income. Let's say, so here will also be income. Then let's say maybe your independent variables are maybe interest rates. You can just put here interest rates. And if you have a different independent variable, you can just edit it. If you have more than 2 independent variables, you can add the number of terms. So, but this is the ARDL model, which was suggested by these guys in 2001, right? Okay, with Johansen co-integration, we already mentioned it. Just some notes here for you. It helps determine if we have long-run equilibrium relationship or not. And like I told you last week, co-integrating relationship exists if there is a stationary linear combination of non-stationary variables. So I mentioned to you last week that if you have, let's say, variables which are non-stationary, and then you combine them linearly, and this linear combination of these variables becomes stationary, it means these variables are co-integrated. And one advantage, again, of Johansen co-integration test is that it's a systems approach, which means it does not discriminate between variables. It treats all variables as endogenous variables. And also, Johansen co-integration can detect more than one co-integrating relationship. And you see, I told you here that it has very strong asymptotic properties. So, based on say Johansen is better than ARDL because it has very strong asymptotic properties. And if you're trying to compare Johansen co-integration test with maybe Engle and Granger co-integration tests, then we can say this is an advantage because the Engle and Granger co-integration tests can detect just one co-integrating relationship, but Johansen co-integration test can detect more than one co-integrating relationship. That's why if we are performing the Johansen co-integration test using the maximum eigenvalue or the trace test statistic, we test those hypotheses sequentially until we reach a point where we can no longer reject the null hypothesis. And at that point, we'll be able to determine the exact number of co-integrating vectors present. I showed you last week. So we can have maybe 1 co-integrating vector or 2 or 3. But the bottom line is that we can determine more than 1 co-integrating relationship using Johansen tests. But with the Engle and Granger co-integration test, we can only determine 1 co-integrating relationship. So this is just some notes I prepared for you. It is giving you the advantages of ARDL, it is giving you the advantages of co-integration, Johansen co-integration, and it is showing you the ARDL model. So you can study it. Okay, so directly I'll go to the practicals for ARDL, the application. If you have that idea now, we can check the application. Let me look for data. ARDL, let me see. ARDL. Okay, let's use this one, ARDL. So I'll take this off. So here is our data. It is time series data from 1997 till 2021, annual data. And here we have 3 variables. We have GDP, economic growth, which is our dependent variable. We have inflation, and we have unemployment. So we are trying to investigate the impact of inflation and unemployment on GDP. So let's assume we have done our unit root tests and we have found a mixed order of integration. Okay, one other thing I'll tell you, I forgot, I'll mention it to you now. With ARDL, if you're using ARDL, you can use ARDL if you have a mixed order of integration, but please make sure your dependent variable is I1. So mixed order of integration means some of your variables are I1 while some of them are I0, but please, your dependent variable should be I1. It should not be I0, it should be I1. Take note of that. Okay, so let's assume that our dependent variable GDP is I1, and then with these our independent variables, maybe both of them are I0, or maybe one is I0 and the other one is I1. Whatever the case, we have a mixed order of integration. So now we want to do ARDL. So first of all, I'll put, let me close this EViews. Save now. So now I'll put my data on EViews. I think from 1997 to 2021, right? Yes. What's happening? You know, 1997 to 2021 data, GDP, inflation, unemployment. What's happening to this my EViews? Why is it coming like this? GDP, inflation, unemployment. Okay. I don't know what's happening to my EViews. I should close this thing here. Okay, let's use log form. You know, of course, it's always advisable to use log because it helps a lot. So generate ln GDP equals to the log of GDP. Inflation, and here I'll put unemployment. So we have our variables. So again, you see 25 observations. It's not really sufficient because you know for time series, it's good to have at least 30 observations. So since our observations are not sufficient, again, it's good to do ARDL. Because like, let's assume we do unit root test and we discover that all our variables are I1. We can do co-integration, we can also do ARDL. But since sample size is quite small, ARDL will work well because it has better small sample properties. But you can try co-integration as well. Okay, so these are our variables: ln GDP, inflation, and unemployment. So let's do ARDL. First, you can come to quick estimate equation, and you just write the variables there. Let's say ln GDP, ln inflation, ln unemployment. You can put a constant either at the end, or let's put it here. After dependent variable, you put constant. You can do like that, or if you don't want to do like that, let me close. Highlight the variables. Start with dependent variable. Inflation, unemployment. Right click, come to open, come to equation, and you directly have your variables there. You see your constant can be either at the end, or you can take it here. After dependent variable, put constant. Now you see our method here is least squares. If you allow least squares, it means you're trying to do ordinary least squares. but we are not doing ordinary least squares. So change it to ARDL. You see ARDL, click ARDL. Now when you come here, the lags are automatically selected for you. Automatic selection, and they're telling you 4 lags. You can leave it like that and try it, but if it does not work, you can come back and specify the lags. At times, if your sample size is not too big, if you don't have sufficient number of observations, then you can try to reduce the number of lags. But let's leave automatic selection. And here, trend specification, non-restricted constant, restricted trend. Let's leave it at restricted constant, since that is what they suggest for us. Don't change anything for now. So just leave it like that and click OK. We have our results. Now, when you have these results, we are not interpreting these results. It is just telling us that like when ARDL, when this model is being estimated, this is the model it has selected, 424, but don't bother about it. We are not interpreting these results. Once you get these results, come to view. If you come to view, come to coefficient diagnostics. Under coefficient diagnostics, you see we have long run form and bounce test, and we have error correction form. Now, first of all, we'll start with the error correction form, or with the long run form and bounce test. I'll tell you something about the bounce test first before we perform it. ARDL bounce test. Bounce test will tell us if there is long run equilibrium relationship or not. Remember, ARDL is telling us if there is long run equilibrium relationship or not, and at the same time it is providing long run coefficients. So the bounce test will tell us if there is long run equilibrium relationship or not. How do we perform the bounce test? When we check the bounce test, we will see the F statistic, and then we'll also see the critical values, right? Critical values. Under the critical values, we'll see the lower bound critical values. We'll see the upper bound critical values. This lower bound is actually the I0 bound, and this upper bound is the I1 bound. So we'll see the lower bound or the I0 bound critical values and the upper bound or the I1 bound critical values. Now we have to compare our F statistic to these critical values. Now, if your F statistic is greater than the upper bound critical value, it means there is long run equilibrium relationship. If your F statistic is less than the lower bound critical value, it means there is no long run relationship. But if your F statistic falls in between the lower bound critical value and the upper bound critical value, then your results are inconclusive. You cannot say for certain if there is long run relationship or not. Okay, maybe I should write it. F statistic is greater than upper bound critical value, then there is long run equilibrium relationship. If F statistic is less than lower bound critical value, then there is no long run equilibrium relationship. Statistic is between lower and upper bound values, critical values, then results are inconclusive. Guys, it should be greater than the upper bound, not the lower bound. It should be greater than the upper bound. If that is the case, then we have long run relationship. It should be less than the lower bound, not the upper bound. Lower bound. If that is the case, then there is no long run relationship. And if it falls in between the lower and upper bound, then it is inconclusive. We cannot say for certain if there is long run relationship or not. Before I continue, I will just tell you something, just for the sake of wording. Integration, long run, equilibrium, relationship. Just for the sake of wording. You should use the right words. Okay, guys, of course, we know co-integration means long run equilibrium relationship, right? That is the, we can also say co-integration means long run relationship. For instance, if you do Johansen co-integration test and you find co-integration, it means you have found long run equilibrium relationship. If Johansen test is telling you that two variables are co-integrated, it means there is a long run equilibrium relationship between these two variables. No problem. We can use those two words interchangeably. Co-integration, long run equilibrium relationship for Johansen co-integration test. But please, for ARDL, don't mention the word co-integration. It's better to use the word long run equilibrium relationship. So don't say there is co-integration. No. Say there is long run equilibrium relationship. If you do Johansen co-integration test, you can say there is co-integration. And at the same time, you can still say there is long run relationship. No problem. Or you can say there is no co-integration. Or you can say there is no long run relationship. It's fine. But when we come to ARDL, just use the word long run relationship. Don't mention co-integration. Why am I saying this? Because technically speaking, we can only do co-integration if all variables are integrated of the same order, if they are all I1, for instance. But you know, with ARDL, we are doing it if there is a mixed order, if there is I0 and I1. So you cannot be talking in terms of co-integration, because you cannot be talking in terms of co-integration when the variables are not integrated of the same order. You understand? So just to use the right word in the right situation for ARDL, especially if you're doing ARDL when the variables are mixed order. If you're doing ARDL when the variables are mixed order, then don't talk about co-integration, just talk about long run relationship. But if you're doing ARDL when everything is I1, remember I told you you can also do ARDL when everything is I1. In that case, you can use them interchangeably. You can talk of co-integration or long run relationship because they are all I1. You understand? So that's just for the sake of wording, using the right words at the right time. Okay. So that is it. Let's check our results. So come to view, coefficient diagnostics, long run form and bounce tests. I open the results. Scroll down. You see the bounce test, the F bounce test. Scroll down. So you see our F bounce test, right? F bounce test. You see the null hypothesis is saying that there is no long run equilibrium relationship. Now, this is our F statistic. F statistic 6.8. We have our critical values. You see a I0. This is the I0 bound, which is the lower bound. This is the I1 bound, which is the upper bound. So for the I0 bound, these are our critical values. at different significance levels. So let's focus on 5%, our usual significance level. So at 5% level of significance, our lower bound is 3.1 and our upper bound is 3.87. Look at our F statistic, it is 6.8. Our F statistic is bigger than the upper bound critical value at this significance level. Since F statistic is greater than the upper bound critical value, it means we can reject the null hypothesis. What is the null hypothesis? It is telling us that there is no long-run equilibrium relationship. So if we reject this null hypothesis, it means we accept the alternative hypothesis, which tells us that there is long-run equilibrium relationship. Exactly what I told you. So because our F statistic is greater than the upper bound critical value, it means we reject the null hypothesis, which says there is no long-run equilibrium relationship, and we accept the alternative hypothesis, which says there is long-run equilibrium relationship. Therefore, there is long-run equilibrium relationship. Don't say there is co-integration. Say there is long-run equilibrium relationship, because we have mixed order of integration. So that's how we perform the F-bounds test. But if this value was, let's say, maybe it was 2.5, then we would have concluded that 2.5 is less than the lower bound. Therefore, we cannot reject the null hypothesis, and we will conclude that there is no long-run equilibrium relationship. But because it is greater than the upper bound, it means there is long-run equilibrium relationship. If this value was maybe, let's say, 3.5, then it would have been in between the lower bound and upper bound. So it is inconclusive. We cannot say for certain. So that's how we perform the F-bounds test. Now, since the F-bounds test has told us that there is long-run equilibrium relationship, we can now go ahead to get the long-run coefficients. And we'll get the long-run coefficients still here on the same page, where you see levels equation. Here are our coefficients. So remember, our dependent variable is economic growth, right? So this is inflation, and this is the coefficient. This is the T statistic, and this is the probability value. So if we check probability value, you see it is insignificant. Even for unemployment, probability value is insignificant. So therefore, we cannot interpret these coefficients. Of course, inflation has negative impact on economic growth, but it is insignificant. You cannot interpret. Unemployment has positive impact on economic growth, but it is insignificant. You cannot interpret. While interpreting these coefficients, you interpret them normally as you interpret coefficients for ordinary least squares. But please don't reverse the signs. Remember, when we're doing co-integration and we solve vector error correction model, I told you that if you're interpreting the long-run coefficients for vector error correction model, you change the signs. For instance, if this is negative, you will say it has positive impact. If this is positive, you will say it has negative impact. That is for vector error correction model. We are changing the signs because of the error correction mechanism. But for ARDL, you don't change the signs. You interpret it normally as with ordinary least squares. So here is negative relationship, here is positive relationship. Whatever the case, we cannot interpret it because they are insignificant. So we will just say inflation and unemployment have no statistically significant impact on economic growth, GDP, right? So you see the advantage of ARDL. It is telling us if there is long-run relationship or not with the F-bounds test. And at the same time, it is giving us the long-run relationship, the coefficients. But with co-integration, Johansen, it will only tell us if there is co-integration or not. But if we want to get these coefficients, we need to do vector error correction. Okay, so that is the long-run form. Come to view, coefficient diagnostics. So we have seen the long-run form, the long-run coefficients, and the bounds test. Now let's see the error correction form. With the error correction form, again, you will still get the F-bounds test. So you can get the bounds test both from the long-run form or error correction form, you will still get the bounce test, still the same F statistic, still the same lower bound and upper bound for 5%, the same thing. But now let's focus on the error correction form. So, of course, you can interpret the short run coefficients if you want. This is like inflation. This D means like short run. This is like 1 inflation, but we are not too interested in the short run coefficients. So let's focus more on this. This is the error correction term. This is the coefficient of the error correction term. You remember when we're talking about the coefficient of the error correction term under the vector error correction model, we said it has to satisfy 3 conditions, right? First, it needs to be negative. Second, it needs to be statistically significant. And third, it needs to be less than 1 in absolute value. If it is not, the first two are very important. It has to be negative and it has to be statistically significant. The third, it has to be less than 1 in absolute value. It's not too strict. It can be greater than 1, but even if it is greater than 1, it should not be greater than 2. Okay. So this is our coefficient of our error correction term, where you see this co-integration something here. First of all, 0.02, which means it is less than 1 in absolute value, and it is statistically significant, but there is a problem. It is not negative. You see, it is positive. It has to be negative. So it means the error correction model here has not worked well. So that is a problem. Actually, it has to work well. But let's assume that this was negative. Let's say here was minus 0.02 and the error correction model worked well. How can we interpret it? How can we interpret the error, this coefficient of the error correction term? I mentioned it to you when we were doing vector error correction model. I will still mention it again now. It shows us the speed of adjustment of the dependent variable towards its long-run equilibrium value following a short-run shock. So whenever there is a short-run shock, whenever there is a shock in the short run, a short-run deviation away from long-run equilibrium value, at what speed does the dependent variable adjust towards its long-run equilibrium value? Now, with the contribution, with the short-run contribution of the independent variables, at what speed does the dependent variable adjust towards its long-run equilibrium value? You understand? So how will I interpret this? In this case, we have two independent variables, right? Inflation and unemployment. And our dependent variable is economic growth. So let's assume that this was negative 0.02. So how will I interpret it? I will say short-run values of inflation and unemployment, that is short-run values of the independent variable, contribute to the dependent variable economic growth converging to its long-run equilibrium value at a speed of adjustment of about 2% every year. So that's how you interpret it. You say short-run values of the independent variables, they contribute to the dependent variable converging to its long-run equilibrium level at a speed of adjustment of about this value. Since here is 0.02, so you will say 2%. Even if here was negative, you will not say minus 2%, you will say 2% at a speed of adjustment of about 2% every year. But remember, this has to be negative, it has to be statistically significant, and it has to be less than 1 in absolute value. But if it is not less than 1, it can be less than 2. So that's how we interpret the coefficient of the error correction term. Whether ARDL or vector error correction model, you interpret it the same. And I'm sure Niga Hoja will ask in the exam, because she likes asking, interpret your coefficient of your error correction model, so you should be careful about that. So that is it. Coefficient diagnostics, we have seen the long run form, that is the long run coefficients. We have performed the bounds test to check if there's long run equilibrium relationship or not. We have checked the error correction form and the coefficient of the error correction term, which is actually the speed of adjustment. So that is it. We can also check the residual diagnostics, and we can check normality, serial correlation, heteroscedasticity. So just come to view residual diagnostics. Let's start with normality. So here is the Jack-Barrett test. You see, you know the hypothesis for Jack-Barrett test, right? The null hypothesis is that it is normally distributed. That is, the residuals are normally distributed. Excuse me. While the alternative hypothesis is that the residuals are not normally distributed. So here you see probability value is 0.7, which is greater than 5%. So we cannot reject the null hypothesis, which means our residuals are normally distributed. Come to view residual diagnostics, serial correlation. So here you can specify the number of lags, but since it is automatically selecting 2, don't change it, just take it like that. And then this is the Bush-Godfrey serial correlation test. Of course, you'll see the null hypothesis. There is no serial correlation at up to 2 lags. Okay. So just check F statistic, check the probability value. Of course, we did this with ordinary least squares. It is the same thing. Check this probability value. It is greater than 5%, so we cannot reject the null. The null is saying there is no serial correlation, so we cannot reject the null. It means there is no serial correlation. Come to view residual diagnostics. Let's see heteroscedasticity. Of course, you know with heteroscedasticity, we have the BPG test, the Harvey test, the Glacier test, the AUTO-REGRESSIVE conditional heteroscedasticity test, and the White test. But the White test, of course, you can perform all these tests and then you go with the majority as we have always done. But if you must do just one test, do the White test, because the White test is the general test for heteroscedasticity. So let's do White test. Don't include cross terms. You can include cross terms, but I don't like including cross terms, so I will take it off. I will take OK. So the null hypothesis is saying that there is no heteroscedasticity, or you can say there is homoscedasticity. And just check, you see here is 0.5, which is bigger than 5%. Therefore, we cannot reject the null. So it means there is no heteroscedasticity, or you say there is homoscedasticity. So in our case, there is no problem. We have found that the residuals are normally distributed. We found that there is no serial correlation, and we found that there is no heteroscedasticity. So there is no problem with the residual diagnostics. Come to view. Let's check stability diagnostics. Come to stability diagnostics, and we can check Ramsey reset test, and we'll check the recursive estimates, the Kusum and Kusum squares. First, let's start with Ramsey reset test. Again, you can specify, but don't change it for now. If it is suggesting 1, just leave it like that. Okay. It is not allowing us to do it. Regressors may be perfectly collinear. It means maybe there is multi-collinearity in our sample. If there is multi-collinearity in our sample, then that's a problem. We cannot perform the Ramsey reset test. That's bad. Let's see. It means our data is not really the best. Of course, our data is not the best because our error correction model did not work well anyway. It was positive instead of negative. Yeah, but I explained that to you. So we cannot do the Ramsey reset test. Okay, but of course, you know the Ramsey reset test, right? With the Ramsey reset test, you have the null hypothesis is saying that the functional form is appropriate, and the alternative hypothesis is saying that the functional form is not appropriate. Am I correct? Let me see. To be sure. Null hypothesis is saying that functional form is appropriate. Yes, I'm correct, I think. Functional form is not appropriate. Yes, because you remember, null hypothesis is saying that there is no problem, while alternative hypothesis is saying that there is a problem. So if you do the Ramsey reset test, you just check the probability values, and then if it is less than 5%, you will reject the null and accept the alternative. But if it is greater than 5%, then you cannot reject the null. We did it when we were doing ordinary least squares, so I don't think that's a problem. So next, I will check. Let me go back to my ARDL model. Next, I will check the recursive estimates. These are actually the most important stability diagnostics, the Kusum and Kusum squares. So if I come to view stability recursive estimates, we have to check the Kusum and the Kusum squares. Kusum stands for cumulative sum. So we'll start with Kusum. I'll click OK. Now, guys, you see the blue line is the cumulative sum, this blue line, and the red dotted line are showing you the critical values at 5%, right? So like this red dotted line, this one is like the upper critical value, and this one is like the lower critical value. While this blue line is the Kusum, cumulative sum. This Kusum line has to fall in between these critical values. It has to be in between this upper critical value and this lower critical value. If that is the case, then we can say our ARDL model is stable. So because you see our Kusum line is in between, it should not touch these critical values. It should not touch it or cross it. Because if this blue line was maybe crossing this value or maybe even touching the value, it means the ARDL model is not stable. But you see our own, it lies in between. So it is stable. That is not a problem. Now that is Kusum. Let's check Kusum squares. So come to view, stability, recursive estimates, Kusum of squares. Now problem. You see the Kusum of squares, you see the line, it crosses this lower critical value, right? It means based on the Kusum of squares, our ARDL model is not stable. For it to be stable, this blue Kusum line should actually be in between. It should be like in between. It should not touch this dotted line. It should not touch it or cross it. It should be in between. So based on this, it means our model is not stable. So if you're doing this kind of study and you find this kind of thing, then maybe you can report the Kusum and don't report the Kusum of squares. Or maybe the reviewers want you to report both. So it's better to find data where both the Kusum and Kusum of squares will fall in between, that is stable. But based on this, our Kusum of squares is telling us that ARDL is not stable. Of course, our data is not the best. We found so many problems with our data. First of all, the error correction model did not work well because it was positive. It has to be negative. Secondly, we could not do the Ramsey reset test because there's multi-collinearity in our data. And then thirdly, the Kusum of squares now is telling us that our model is not stable. So it means our ARDL model is not stable. Our data has problem. Okay, so I think that is it. I've shown you coefficient. Let me see, is there anything I should show you? No. Residual diagnostics. We have done stability. Okay, so that is it. So just to summarize everything, as a first step for time series analysis, first thing, run unit root tests. You have the augmented decay Fuller and the Phillips Perron unit root test, and you have the KPSS stationarity test. Do these tests, and then you have the order of integration. If all your variables are I0, you should do ordinary least squares basic regression. If all your variables are I1, you should do co-integration, Johansen co-integration test. If you have a mixed order of integration, which means some of the variables are I0 while some of them are I1, then the only thing you can do is ARDL. That's the only solution, ARDL. Now, with I1, if everything is I1, even though Johansen is the best, but you can also do ARDL. So you can also do ARDL if everything is I1. But bear in mind that Johansen is the best. If you must do just one of them, it should be Johansen, unless you have a very small number of observations, then I will recommend ARDL in this case, because ARDL has better small sample properties than Johansen. But if you have a high number of observations and you have I1 and you must do just one test, then do Johansen. But in most studies, they do both of them. They do Johansen and ARDL. Maybe Johansen is the main method, and then you can use ARDL as the robustness to check the robustness. So you can do both of them, no problem. But then know that why, despite the fact that Johansen has better asymptotic properties than ARDL, but know that ARDL also has advantages over Johansen. For instance, Johansen only tells us if there is co-integration or not, but it does not give us the long-run coefficients. That's why we have to do vector error correction model to get the long-run coefficients. But ARDL will not only tell us if there is long-run equilibrium relationship or not, it will also provide us with the long-run coefficients. You understand? That's an advantage. So you have to be careful about that. Now, if you're doing the ARDL model to determine if there is long-run equilibrium relationship or not, we have to perform the F-bounds test. If you're performing the F-bounds test, you are comparing the F statistic to the critical values. If your F statistic is greater than your upper bound, that is your I1 bound critical value, it means there is long-run equilibrium relationship. But if your F statistic is lower than the lower bound critical value, it means there is no long-run equilibrium relationship. If your F statistic falls in between the lower and upper bound critical value, then it is inconclusive. You cannot say for certain if there is long-run relationship or not. And I also told you that just to be sure you're using the correct wording, if you're doing ARDL where you have a mixed order of integration, then don't say there is co-integration. Rather, say there is long-run equilibrium relationship. But if you're doing ARDL where everything is I1, then you can talk about co-integration, no problem. But the bottom line is that we should use the word co-integration if everything is I1. We cannot use the word co-integration if we have mixed order of integration. Why? Because technically speaking, we can only do co-integration if all our variables are integrated of the same order. So you cannot be doing ARDL where you have a mixed order. Everything is not the same order, it is mixed, and then you're talking about co-integration. So it's better to use the term, the wording, long-run equilibrium relationship, rather than saying co-integration, even though we know that co-integration means long-run equilibrium relationship. Understood? So if you do the F-bounds test, and you determine that there is long-run equilibrium relationship, you now check the level equation, you get the long-run coefficients, and you interpret them normally as you interpret ordinary least squares coefficients. Don't reverse the signs. We only reverse the signs for vector error correction model. Now, after you're done with the long-run form, also check the error correction form, and then you see your coefficient of your error correction term. It has to satisfy 3 conditions. Most importantly, the first 2. First of all, it should be negative. Secondly, it should be statistically significant, and it should be less than 1 in absolute value. Or if it is not less than 1, then it should not be greater than 2. No problem. If all these conditions are satisfied, then it means your error correction model has worked well. And if you're interpreting the error correction term, the coefficient of the error correction term, it is the speed of adjustment of the dependent variable towards its long-run equilibrium level following a short-run shock. That is, the short-run values of the independent variables contribute to the dependent variable converging to its long-run equilibrium level at a speed of adjustment of about this percent every year. So be able to interpret this coefficient of the error correction term the speed of adjustment, because Nigahoja most probably she will ask in the exam. She likes asking it anyway. So if everything is fine, now you should check your diagnostics. Check the residual diagnostics. We'll check serial correlation, the Lagrange multiplier test, Bush-Godfrey. Check heteroscedasticity. You can check all the tests, or maybe you can do just the White's test, since it is the general test. You can check the Jack-Berra normality test, and then now you can go to the stability diagnostics. You can check the Ramsey reset test to check if the functional form is appropriate or not. And most importantly, you have to check the recursive estimates, the CUSUM and the CUSUM of squares. Now, with the CUSUM and CUSUM of squares graphs, the plots have to fall in between the lower and the upper critical values. They should not touch or cross the limits. If they fall in between, it means your model is stable. But if they touch or cross the limits, lower or upper limit, it means your model is not stable. So that is it for the auto-regressive distributed lag model, ARDL. So guys, I wish you all the best for your exams. If you have any questions, you can always contact me on Teams, or you can come to the office if you like, we can discuss. Most probably we'll give you your term assignments, term project, where I'm sure you will have to do something related to time series, maybe co-integration, maybe ARDL, we'll see. So I wish you all the best and good luck. Okay, so I'll stop recording now. Let me see. First of all, I should stop sharing. Then next, stop recording. Stop recording. Where is it?